Now we'll look at the next type of expansivity as volume or cubic expansivity. This is the increase in volume of a substance, per unit volume, per unit rise in temperature. The volume of this substance is increasing by 1 unit as a result of increase in temperature by 1 unit also of the temperature. Are you getting it? So we have it that this is known as volume expansivity. It is given by the formula gamma is equal to change in volume over original volume times rise in what? Temperature. For instance, you have this as a bar, a solid material. The length is increasing, the area is increasing, the thickness is also what? Increasing. So now when we talk about volume expansion there, but they're increasing by 1 unit, by 1 unit of the original volume, as a result of increase in what? Temperature, by increasing the temperature of the original temperature of that object by 1 degree. Is that okay? Either 1 degree Celsius or 1 Kelvin. So that brings about volume expansivity. From this, we have the formula to be change in volume over original volume times rise in what? Temperature. So how V2 is final volume, V1 is original volume. So V2 minus V1, that is change in volume now, but V1, which is original volume, times rise in temperature, which is theta 2 minus what? Theta 1. Where V1 is initial volume at temperature theta 1, when you have not added heat to it. Now V2 is final volume at temperature theta 2, you have added it now, that led to what? Expansion of these solids. Now change in theta gives you change in temperature, which is theta 2 minus what? Theta 1. Is that okay? Now from the equation we'll have there, from this equation we'll have, if you cross multiply here, is equation 1, we're going to have V2 minus V1, as is this, is equal to, we'll have gamma into V1 change in theta. You can say it, gamma into V1 change in theta. So of course multiply. We want to get our V2 when you have added heat. So V1 minus V2 is equal to gamma V1 change in theta. Instead of writing theta 2 minus theta 1, already that means change in what? Theta. So V2 is equal to gamma V1 change in theta plus V1, because this minus V1 crosses over this equality sign, it turns what? Plus V1. So V1 here is common, so we now take one of them. We have V2 is equal to V1 gamma change in theta plus 1. Because if you now expand, you have V1 change in theta, V1 gamma change in theta, which is this one. This multiplied by this gives you back this one. So we have V2 is equal to V1 gamma change in theta plus 1. We can rewrite this to be V2 is equal to V1 into 1 plus gamma change in what? Theta. Where increase in volume or expansion is equal to V2 minus what? V1. So the whole of this gives you the what? The expansion itself. V2 minus what? V1. While ordinary V2 is the final volume, when you must have added what? Heat to it. Now I want to see how linear expansivity, area expansivity and volume expansivity are related. So we have a relationship between alpha, beta, and gamma, how they are related. Using a metal sheet of length L1, a metal sheet of length L1 and breadth B1. When the metal sheet is heated through a temperature theta, a temperature rise theta, the length and the breadth became L2 and what? B2. Initial length of this metal sheet is L1. Initial breadth is what? B1. When you now increase the temperature, it is now heated, the original length becomes what? L2. No, the final length becomes, sorry, L2, while the final breadth becomes what? B2. Recall that area normally is length times breadth. That is L times B abbreviated. And we'll have it that the initial area of this metal sheet is A1. And A1 now means the original length times the original breadth. And the final area of the sheet is equal to A2, means final length times final breadth. And from the equation we have derived today, we'll have it that final length gives you initial length into 1 plus alpha change in what? Theta. Therefore, if L2 is this, our B2 will now give us B1 into 1 plus alpha change in theta. Is that okay? Therefore, if that is the case, A2 will now give us L2 B2. Mean L2 times what? B2. Final length times final breadth. And our final length L2 is equal to L1 1 plus alpha change in theta, this one. And our B2 times B1 now into 1 plus alpha change in what? Theta. Now, if we multiply 2 of them, we'll have it that A2 gives you L2 B2, which is equal to L1 B1. And now factorizing, L1 B1 is this, into 1 plus alpha change in theta, bracket opens again for this one, 1 plus alpha change in theta. Now, I want to factorize these two in brackets. So we're using 1 here to factorize this. We'll have 1 into 1 plus alpha change in theta. You close the bracket, plus what is now remaining here is plus alpha change in theta. We'll have plus alpha change in theta into 1 plus alpha change in what? Theta. We have now factorized this, so we want to multiply out now. 1 times 1 gives you 1 here, plus 1 times alpha change in theta gives you alpha change in theta, plus alpha change in theta times 1 gives you alpha change in what? Theta. Plus what is now remaining is alpha times alpha gives you alpha squared. Are you following it now? So change in theta times change in theta gives you change in theta squared. Now we have 1 plus, you have alpha change in theta, there are 2. You now have 2 into alpha change in theta plus alpha squared change in theta what? Squared. So that gives that A2 now is equal to L2 B2, which is equal to L1 B1 into 1 plus 2 alpha change in what? Theta. So that gives us our A2. And since the value of alpha is very small, for instance, for lots of aluminium, we'll have 0.000026. It is so small, very small, can be negligible. It implies that alpha squared, now when you square this value, for instance, is extremely small and can be what? Neglected. So if it can be neglected now, you want to compare A2 now, so as to know what is the value of alpha. How is alpha, beta, and gamma related now? So A2 is equal to L2 B2, which is what we've gotten here today. We have A2 is equal to L2 B2, which is equal to L1 B1. This is what we have gotten here before now, into 1 plus 2 alpha change in theta. Now we'll have it, we're going to compare it now with what we have here in our area expansivity. With our area what? Expansivity. So we'll have A2 is equal to A1 into 1 plus alpha change, no, beta change in theta. That is our normal area expansivity. So comparing it with this, we'll have, this is A1 already. Then we'll have 1 here. The whole of this 2 alpha gives you what? Beta. and then we have change in theta. So it implies that beta is twice the linear expansivity, that is 2 alpha. Therefore, if beta is twice this linear expansivity, therefore gamma is what? 3 times the what? Linear expansivity. Now I want to see how we can use these formulas derived to solve problems, to see how alpha, beta, and gamma are related. I have example 1. The linear expansivity of the material of a cube is 12 times 10 to the power minus 6 per Kelvin. If the length of each side of the cube is 10 cm, find the area of one face of the cube and the volume of the cube when its temperature is raised to 30 Kelvin. I want to analyze the question and bring out the values we have in this question. Now the alpha there, the linear expansivity, is 12 times 10 to the power minus 6 per Kelvin. You can see it here. Now change in theta from here we'll have is 30 Kelvin. You understand? So if the length of each side of the cube is 10 cm, find the area of one face of the cube, and the volume of the cube when its temperature is raised to 30 Kelvin. So the change in temperature here is what? 30 Kelvin. Then the length of each side of the cube is what? 10 cm. From what we have in that question. So from the initial area of a face of the cube, one face, will now be A1. Meaning A gives you 10 times 10. It's a cube. So we have 10 times 10. So giving you what? 100 cm squared. As the face, one face of it. Initial volume of a face of the cube, V1 now, will now give you 10 times 10 times 10. That gives you 1000 cm what? Cube. Are you following it? So you're asked to get what? In this question, finally, you're asked to calculate, find the area of one face of the cube and the volume of the cube when its temperature is raised to this. So I've only gotten this on this one here as initial area, as initial temperature. But we want to get these values now as the final temperature. But beta is equal to 2 alpha. Meaning that we have 2 times 12 times 10 to the power minus 6 per Kelvin. Giving you 24 times 10 to the power minus 6 per Kelvin. And gamma is 3 alpha, meaning 3 times 12 times 10 to the power minus 6 per Kelvin. And that gives you finally 36 times 10 to the power minus 6 per Kelvin. Now, how do you at last get your A2 and V2? You're asked to get A2 at temperature 30 Kelvin. Your V2 at temperature what? 30 Kelvin. So using the formula A1, A2 is equal to A1 into 1 plus beta change in theta. That is our A2 at temperature 30. So we have A1, we have got A1 to be 100. From here, we got our A1 is what? 100. So we'll put it back here. Into 1 plus 24 is our beta now. Look at our beta is 24. You can see it. 24 times 10 to the power minus 6 is our beta. The change in theta is 30 Kelvin. So I assume that initial sign is 0 Kelvin to final temperature, which is 30. 30 minus 0 is what? 30. We have 30 Kelvin. So if you multiply out the whole of this plus this, multiply by 100, finally will give you 100.072 cm squared. You multiply this out first. Plus 1 times 100, you have 100.072 cm squared. Also, V2 is equal to V1, you can remember this formula, into 1 plus gamma change in theta. So our V1 we have calculated is, our V1 is 1000 cm cube. Look at it here, into 1 plus, our gamma is what? 36 times 10 to the power minus 6. You put it back here, times change in theta, our temperature change is what? 30 Kelvin. So multiply this 30 by 36 times 10 to the power minus 6 plus 1 times 1000 gives you 1001.08 cm squared. So this gives you the area of this face, one face of the cube, and the volume of the cube when the temperature is raised to what? 30 Kelvin. Is that okay? This is question number 1. Number 2, example 2, a glass bottle has a volume of 10 raised to the power 4 cm cube at 10 degrees Celsius. Calculate its volume when it is heated to 30 degrees Celsius. So alpha of this glass is 9.0. That is the expansivity of the glass is 9.0 times 10 to the power minus 6 per Kelvin. Now, we want to get, you have to find its volume when it is heated to 30 degrees Celsius. The initial temperature is this. So V1, initial volume at this is 10 to the power 4 cm cube in 10,000 cm cube. Theta 1 is 10 degrees Celsius. Theta 2 is what? 30 degrees what? Celsius. V2 is what we don't know, which is what we're asked to calculate. And alpha of this glass is 9.0 times 10 to the power minus 6 per watt Kelvin. Now, how do we get our V2? Remember, the formula for V2, we have gotten it to be V1 into 1 plus gamma change in theta. So we need to get gamma first. Already we have our V1 and we know our this. So to get gamma, we have gamma is equal to 3 alpha. So I mean 3 times 9.0 times 10 to the power minus 6 per Kelvin. This is our gamma. So if we multiply 3 by this, we have 27. 3 times 9 is 27 times 10 to the power minus 6 per Kelvin. Now we have gotten our gamma to be this. But gamma on its own is equal to V2 minus V1 all over V change in theta, which if you multiply, you have V2 minus V1 is equal to gamma V1 change in theta. We have arrived before now at the formula that V2 is equal to V1 into 1 plus gamma change in theta, which is from here we can now factorize. But if here crosses over becomes plus V1, which we take a common factor of V1, and we'll have this. We have arrived at this formula before now. Substituting the value of V1 into this and gamma, we'll have V2 is equal to 10,000. Your V1 is what? Your V1 is 10,000. Meaning 10 to the power 4 is 10,000. Yes. So we'll have 10,000 into 1 plus. Gamma is 27 times 10 to the power minus 6, which is what we have here. Change in theta is what? 20 degrees Celsius, because 30 minus 10 gives you what? 20. Is that okay? So we'll have it 20 here. So if you multiply 20 by 27 times 10 to the power minus 6 plus 1 multiplied by 10,000 gives you 10,005.4 cm cube. So this gives you your what? V2. So we can see how we can substitute the value of gamma, beta, and alpha. We can use it to solve some problems.